There's kind of a couple different ways to deal with this one. So we need to, in order to push these two things together, they have to have a common denominator. You have two ways to do that. I'm looking at two ways. One way is what we did yesterday, where I look at, okay, this is actually sine over 1, and I can just multiply the top and bottom by the other's denominator. So if I multiply this left-hand side by the other's denominator, I multiply the top by sine x, I multiply the bottom by sine x, and for this one, I'd multiply the top by 1 and the bottom by 1, because this denominator is just 1. So that's going to give me sine squared x divided by sine. And we'll have plus cosine squared x over sine x. Now I said there's another way. The other way is just to, okay, how do I have sine x as a denominator of sine x? Well, this has to be sine squared x. I do like looking at the other denominator because it's going to work more often than just kind of guess and checking your way through it. So I'm going to stick with multiply by the other denominator to create a common denominator. Now we have a common denominator. Remember, when you add fractions, you add the numerators, not the denominators. The denominators stay. So this is just going to equal sine squared plus cosine squared x. I should put my x's on there. All over sine x. And then I should stop and go, wait, sine squared plus cosine squared equals 1. That equals 1. So now I have 1 over sine x. I don't want to deal with that fraction, so we just got to remember the reciprocal of 1 over sine is cosecant x. So the correct answer was D, cosecant x. Sure. Questions on the bell work? Then let's go over any questions we had from last night's homework, the 7.1c, I believe. Yeah, go. Number 4. Number 4 is a really good one to do together, so I'm glad you asked about that one. So I have tangent cubed x minus secant squared x times tangent x all over cotangent negative x. Maybe the first thing I'm going to deal with is that negative sign. Just to get out of the way, you can't have a negative in those parentheses, so I'm going to pull that negative out. Remember, if it's cosine or it's secant, you just put a plus there. But in order for me to put a plus there, I must pull that negative out front. Took care of that. Now, I know we have rules that sometimes we can just change everything to sine and cosine and see what happens there. But my problem is this tangent cubed? I don't like cubes. Cubes don't work. I don't have cube stuff on my sheet, so I need to make that squared. So we need to take it out. Now, the way we could take it out is we can look at the numerator. Is there a tangent in every element in the numerator? Yes. There's a tangent cubed. And when I talk about elements, I'm talking about things that are attached by multiplication. So that means there's a tangent here. Now, just to understand what I'm talking about, if there was a plus 1 here, there would not be a tangent in all the elements. I couldn't do what I'm about to do. But it's not there. So what I'm going to realize is we have a tangent here. We have a tangent here. So we're going to bring a tangent out front. So this is just going to equal tangent x times, well, if I pull it, so remember a tangent cubed is tangent times tangent times tangent. If I pull a tangent out, I'm left with tangent times tangent, or just tangent squared. And then I'm just left with the secant squared x, and everything's over a negative cotangent x. All right, now I'm looking at tangent squared and secant squared, and this is why we need to have this stuff memorized. That's one of our identities. We have an identity that says 1 plus tangent squared x equals secant squared x. I remember that because cotangent goes with cosecant. So tangent goes with secant on this one. Well, to have a negative secant, I would need to move the secant to the left-hand side, which would give me 1 plus tangent squared x minus secant squared x equals 0 right now. But I need this to be alone, so I need to move that 1 to the other side. So moving that 1 to the other side will then give me tangent squared x minus secant squared x equals a negative 1. So if I ever see anything that says tangent squared minus secant squared, we're not memorizing these, okay? We're not memorizing the variations. This you can do on your own. We're memorizing the 1 plus tangent squared. So when I say this, I write this every single time. So now I can go back here and go, oh, you know what? Tangent squared minus secant squared. I'm going to replace that entire thing with a negative 1. So this whole thing gets replaced with a negative 1. Well, that means I really have a negative tangent x over a negative cotangent x. Well, that means it's positive. And cotangent we can write in terms of tangent. You could rewrite all this in terms of sine and cosine, but I don't need to for this one. Because I can just notice that tangent and cotangent are very closely linked, that I would have, well, this would be tangent x over 1 over tangent x. And now I can do keep, change, flip. Keep the top. Change the sign of multiplication. Flip the bottom one. Well, that's just tangent x times tangent x, which will be tangent squared x. Is that enough? Good? So here's your key sign there. If you see something cubed, I can't say all the time, but in this class, like 90-some% of the time, if you see something cubed, you probably have to factor it out somehow so you can take it to that squared power. Now, this is a good example of, did I ever change anything to terms of sine and cosine? No, we don't have to do that to simplify. That was just one of the tools we can use. So if I got to a place where I couldn't do anything, then I'll turn it to sine and cosine and see if I could do another method. So that's just a method we've been using. Okay? More questions? Yeah? Sure? Number 8, do you mind if I change those u's into x's? Okay. So I have 1 plus sine x all over, it looks like sine x, plus our cotangent x minus cosine x all over cosine x. Now, we don't have to do this, but Jason, what I'm picturing here is, do you see how everything is in terms of sines and cosines? And all of a sudden you have this cotangent just hanging out there. It's like different. Here I had nothing but tangents and cotangents, so I had no real reason to change it. But either in my mind or on the paper, I need to start picturing that that cotangent is actually cosine over sine. I won't write it yet, but in my mind, I'm like, that sticks out like a sore thumb. So in my mind, I'm like, this seems weird. This seems weird. But whether it's weird or not, I know my first step is to push these two things together. So that means I need to multiply the first one by the other denominator. So I'm multiplying that first one by, let's do this in kind of a light purple. So I'm multiplying the top by cosine over cosine. Multiplication. And I'll multiply the other one by sine x over sine x. Jason, do you get why I'm doing that? Because I want to push those two things together, so I multiply by the other denominator. Now, I'm not going to distribute until I know for a fact I have to distribute. So what I mean by that is this is going to equal, the top part will be cosine x times 1 plus sine x. Didn't distribute it. Just leave it alone, and that will be all over. I'm just going to leave that as cosine x sine x. For my other one, I'm going to pull that sine x out front, which will give me sine x. I'm going to leave a blank for that cotangent for just now. But we have cotangent minus cosine x all over cosine x sine x. Now, the reason why I might put a blank there is maybe now I start thinking about cotangent as being that cosine over sine. And the reason why I'm thinking that is, well, if this is cosine x over sine x, I can start seeing if I distribute this, this will cancel out. Let's just push these things together first, and then we'll take care of that. So I have cosine x times 1 plus sine x plus sine x times that cotangent, which I changed to cosine x over sine x, minus cosine x all over cosine x sine x. Now that looks all confusing and stuff, but really I just used algebra. I used algebra to multiply by the other denominator, and I just added these things together. Just don't lose track of your sines and cosines. Well, I always say don't distribute unless you have to. It looks like I have to because I can't just cancel this stuff out. There's nothing that really cancels out. So let's go ahead and we'll distribute this stuff and see what happens from that. So that make sure you distribute the entire thing to both things. So that's going to give me a cosine x plus, I'm going to have cosine x sine x. Now when I distribute that sine, the whole reason why I changed this over is because this will cancel out. I'll just be left with cosine x on top. So we'll have plus cosine x. And then we'll have a minus. Looks like I'll have a cosine x sine x as well. All over this cosine x sine x. Did I start with the right thing? Yeah, we're good. Okay. So now I'm going to notice these two things. See this plus cosine x sine x and this negative cosine x sine x? Sometimes you'll have these reversed where you see this is sine x, cosine x. Remember, you can always flip them. Make them match up. So those two things are going to cancel out. And I have cosine x plus cosine x, which equals 2 cosine x is on top, and I have a cosine x sine x on bottom. Now, my top is all connected by multiplication. So is my bottom. So I can cross out these cosines, and I really have 2 over sine x. But when I have a fraction with sine, I'm picturing, okay, 1 over sine is really cosecant. So I'm going to take a leap of faith. Tell me if this doesn't make sense, but I'm going to write this as 2 cosecant x. Are you okay with that? Okay. So that'll be 2 cosecant x. Is that a lot of steps? Yeah, but it's all basic algebra. The only thing you really needed to know from this class was cosine over sine. Everything else is algebra, just with different letters and x and y's and numbers and these things. But the only thing you need to know was cosine over sine, realistically. Yeah, Ernie.
How'd you get
2 cosecant x? Here?
Yep.
See how I had this cosine and this cosine?
Thought it was cosine squared.
Not when you add it. When you multiply, it becomes cosine squared. When you add it, you're just saying how many you have. I have 1, 2 of them. If this was attached by multiplication, then I would agree it's cosine squared. But when you add them, you just count how many you have. It's just like x plus x is 2x. X times x is x squared. Okay? So if you ever get confused at all, just think about, what if these were just x's? What would I do with it? Oh, if you add it, it becomes 2x. Same thing with cosine. You have 2 cosines. That's what I'm saying. That the easiest part about this is trying to relate it to just algebra skills and trying to get away from that. It's just the pre-calc stuff. Yeah.
Is the 2 separated from the cosine x?
Right here?
Yeah.
Well, it's connected by multiplication.
Okay. So when you take out the cosine x, it's just 2 left.
It's just 2 left. Yep. Just like if I had 2x divided by x, the x cancel out, I'm left with 2. Any other questions?
Could you do 5?
I could do 5. Five gets back to that same point I tried to drive home yesterday in the fact that I have two fractions. I'm going to change it to x, okay? It's just easier to write that neater for me. So I'm going to notice I can't push those fractions together until they have a common denominator. Easy way to create a common denominator is multiply by the other denominator. So if I'm fixing to change this one, I'm going to multiply by the other denominator. But there could be an easier way for this one. I can multiply it by sine x squared or sine squared x. So you can multiply this top by sine and get sine to the fourth. Multiply this one by sine cubed and get sine to the fourth. But you might realize a nice little shortcut here in the fact that I could just multiply this bottom one by sine squared x. That would give me my sine cubed, which means all I have to do is the same thing to the top. Okay, so now we have 1 over sine cubed x minus cotangent squared x times sine squared x all over sine squared x, which will lead me, cubed x, because we did do sine squared times sine x, which would be sine cubed x, which gives me 1 minus cotangent squared x sine squared x all over sine cubed x. Something stands out to me here. Bless you. I have a lot of signs on there, and all of a sudden I have this weird cotangent. So if you're ever stuck, just change things in terms of sine and cosine. Like I said, that's a nice fallback. We learn that first because that is always our go-to. If I don't know what to do next, and I have a bunch of sines and cosines, change everything to sines and cosines. So we can go ahead and change this to 1 minus cosine squared x over sine squared x times sine squared x. I might put it as sine squared x over 1. It helps a lot of us. All over sine cubed x. We're going to see our sine squareds actually cancel out. And also I have 1 minus cosine squared. 1 minus cosine squared says sine squared plus cosine squared equals 1. And what is, you said it right.
Sine.
It's just going to be sine squared. Yeah, it's going to equal sine squared. Because if I do a little work off to the side and go, if I have sine squared x plus cosine squared x equals 1, I move the cosine over. Sine squared x equals 1 minus cosine squared x. So I can replace that 1 minus cosine squared with sine squared. Now remember what cubed and squares mean. I have sine times sine. On the bottom I have sine times sine times sine. 2 of the ones on top cross out with 2 of the ones on bottom.
So it's just 1 over sine.
Yep.
Sine x.
It's going to equal 1 over sine x, which equals cosecant x.
On the test, will you allow us to change the variable to whatever we
Yeah, I don't care.
Okay.
There's only certain instances that you have to change. So sometimes we'll have an alpha and a beta. You have to change something to x and y.
Okay.
Okay, any other questions? I bet you for people that are practicing, even though when you go through these, you're stuck, people that have been practicing, I hope this stuff makes sense as I go through it. You're like, yeah, I probably could have done that. And now hopefully you can do it next time you see a problem like this. For people not doing the homework, some of this might just seem like gibberish. You got to practice this stuff so in class things are like, okay, that makes more sense now that I see it. I got stuck here. What do I do if I get stuck? I do what Mr. Pabian did and try these certain things. But if you haven't tried it at all, you're just copying this down. Got to try it. Know where you get stuck. because my goal is to help you get unstuck in those situations. Because we'll all get stuck on problems. We just have to know the different tools that we can use to get unstuck. And that's a lot what we're doing today. But before we start today, are there any last second questions? Okay, then today I'm going to throw a new word at you. It's called verifying identities. This lesson is not entirely just verifying. In fact, only the last couple questions are verifying. We're going to go through some more tools that we can use. They're tools we've already used, but we'll define them a little bit more. So verifying, to verify, it means to prove that both sides of an equation are equal. Now, we have some rules when we verify things. First of all, we need to choose a side of the equation to start with. We will do as much as we can on just one side before we even look at the other side. So we pick a side. We usually pick the most complicated side. It's easier to break things down than to kind of build them all up out. So we usually pick the more complicated side. Then we're going to simplify this side until it reduces to the other side. We're going to use our trig identities in algebra to make one side look like the other. 3 says never work on both sides at the same time. What I mean by that is you can no longer subtract 2 from both sides. You can no longer add 2 to both sides, divide by 2 on both sides. You have to, and this is what I do, I build a wall between them. I build a wall between them, and whatever work I do on this side stays on this side. So I work on this side as much as I can. If I need to, I can then go to this side and maybe change this side to make it look like. Our goal is to make sure both these sides look the same without, like I said, you cannot subtract 1 from both sides. I can't move anything from here to here. These are basically proofs. I want to prove that this equals secant squared. It doesn't work when you start subtracting stuff. So our goal is really, we were practicing simplifying stuff, right? This is basically telling you simplify this side, and it tells you exactly what you should come up with. So verifying can actually be a more simplified simplifying, because you know what your answer needs to be. So if I pick the left-hand side to work with, I know it has to equal a secant squared. Now we run through a list of things we know how to do. Do we have fractions to push together? Not right now, we don't. So we're not going to do that. I'm not going to push fractions together. I have nothing to factor out. So I always go on old reliable first. Change things to sine and cosine and see what happens there. That's the old reliable. I have nothing else I can really think of doing. Let's change everything to sine and cosine. So that means we are going to have 1 plus, oh boy, secant. Is that cosine or is that sine? Cosine. It's cosine. Okay, so it'd be 1 over cosine. Now, sine doesn't change, so I'll just change it to just sine x over 1, because sometimes it's nice just to have everything as a straight-up multiplication. Tangent, is that secant over cosine, or is that cosine over sine?
Oh, sine over cosine.
What did I say?
Is it cosine over sine or secant over?
Oh, I'm sorry. Okay, fair enough. Is it cosine over sine, or is it sine over cosine?
Cosine over sine.
It's sine over cosine. Now remember, my advice to you is, I always think of what cotangent is. Cotangent is cosine over sine. You have the 2 hard k. Just like 1 plus cotangent squared equals cosecant squared. So if you're ever deciding between which one, I always go through cotangent first. So if cotangent is cosine over sine, then tangent must be sine over cosine. Okay, well, we got a whole bunch of multiplications here. Remember, multiplication goes straight across, which means I have 1 times sine, which should be sine squared. Cosine times 1 is cosine. Cosine times cosine is cosine squared x. Oh, hang on. What's sine over cosine equal? Tangent. So if I have sine squared over cosine squared, I can change that to tangent squared. Hold the phone. I have a 1 and a tangent squared. That probably has a Pythagorean identity. What does 1 plus tangent squared equal?
Secant.
It equals secant squared. And now what we have to do is say, I'm not going to rewrite secant squared over and over and over. I'm just going to put a little arrow and go, those things are equal. Got it. Put a little check mark. That's it. Nailed it. So the one good thing about verifying is you know what you need to get to. So it's almost like a multiple choice. Either you get to it or you don't. But here's my advice to you. Don't make up rules to force it to happen. You can get stuck and still get most of the points. If you start making stuff up, everything you make up, I subtract more points from. So you might have done everything right, and all of a sudden you make stuff up to make it work, and you're going to lose a point for everything you make up. Yes?
Can you change the right side?
You could change the right side. It's harder.
But it just has to equal.
It just has, so there is a possibility, because you could say, oh, you know what, secant squared equals 1 plus tangent squared.
Yeah.
I could write 1 plus tangent squared as 1 over and break it all the way, but that's really hard to do. I don't know many people that could do that. It's much easier to take the more complicated side and make it smaller. All right. That's the only verifying we're going to do in class. You have some for homework, but today is basically some rules that maybe we forgot. We talked about it along the way, but now let's formalize a bunch of the rules. First rule we need to keep track of: difference of squares. If I see, okay. If I see something that's like 1 plus tangent times 1 minus tangent, yes, we could distribute it. We could use our FOIL, we could use our box method, we could distribute the 1 to both things, the tangent to both things. But more efficiently is to realize that that is a difference of squares. They're the exact same thing, except they have a plus or a minus inside of them. So we should just be able to write this as 1 squared minus tangent squared x. And perhaps we shouldn't even put the 1 squared. We should have a 1 minus tangent squared x.
So you just got rid of the middle terms.
What was that?
Did you just get rid of the middle terms?
I did. The middle terms will subtract.
So what is it, the A and B?
That's a plus b times a minus b.
Okay.
Yep, that's a difference of squares. Now, if you factored it out, like Mercer said, if I would have factored this all out, my middle terms would have just got subtracted and I would end up with the same solution. But it saves time and it shows up so many times that it's worth memorizing and knowing how to do that. Does this say anything about simplifying it? Just says read the directions for your homework carefully. I will go over those. In fact, we'll do that right after of what I'm expecting. Some of these we don't need to simplify. So that's it. That is and maybe I'll put that above because it was noted. It's a plus b times a minus b equals a squared minus b squared. Okay, another thing that tricks people is this little squared thing. They think it distributes in here. It does not. JP, do you have a question?
Oh, no.
Okay. All right.
Just makes 2 of them.
It just makes 2 of them. So we should have 2 sine alpha plus 1 times 2 sine alpha plus 1. Here's the next thing that trips up people. Is this a plus and a minus?
No.
No. So you cannot use difference of squares. This difference of squares would only work if this was a plus and minus. That's not what it creates. You have to distribute these. I don't care what technique you use. I only teach one method. You can put the box method. You can do whatever you want. I only teach one method because it works for things that aren't just binomials type binomials. I take the first term and I distribute it to the 2 other terms. So I take 2 sine alpha and multiply it by this 2 sine alpha. That's 2 times 2, which would equal 4. Sine alpha times sine alpha would be sine squared alpha. Then I take that first term and multiply it by the 1. 2 sine alpha times 1 is just 2 sine alpha. Done with that. If this was 3 terms, I would do it to all 3. If it was 4 terms, I would do it to all 4. Then we move on to the next term, and I always go underneath and I go, oh, I just forgot to distribute this 1 to both things. So now I have 1 times 2 sine alpha, so that would be a plus 2 sine alpha. 1 times 1 is 1 squared, which is still just 1. This whole thing equals 4 sine squared alpha plus 4 sine alpha plus 1. Done. Just told me to multiply it. That's it. If you know how to multiply binomial times binomial, then I didn't really. Because all it asks you to do is multiply. And I'll go over the homework with you and tell you what I'm looking for. Okay, then if we come down here, it says factor each expression. It says factor each expression. It doesn't say anything about simplifying it. So this is a squared minus b squared. So you might have realized that this is actually just equal to 1, but it didn't ask us to do that. It asked us to factor this. Factoring something that's a squared minus b squared would factor into secant x minus tangent x times secant x plus tangent x. So there are times where we don't do the obvious thing, where I don't. So when I verify something, I have to make it look like the other side. If the other side doesn't have a 1 in it, I might have to factor it this way. Does this happen a lot? No. But might it happen? Yes. Just like our next one. Our next one, we might have been pretty comfortable with going, 1 minus sine squared, that equals cosine squared. That's true. This is true. So I could put these in pink to say that these are true statements. But that's not what they're asking me to do. They're asking me to factor it. So to factor this, you have to remember that this really is a squared minus b squared. Where I can rewrite this as a minus b times a plus b. So it is 1 squared minus sine squared. So if I was asked to factor this, I could change this to 1 minus sine x times 1 plus sine x. You're just good with not knowing this stuff?
No, I do that.
Okay. And then let's do big factoring. We're going to do a guess and check, and this will be the first time in class we're going to have ones that we can't guess and check. And I'll go through my method of doing that. I'm going to use factor by grouping. All right. So sometimes my advice is replace these with just x's. So instead of picturing this as sine squared plus sine b minus 2, we could picture this as being x squared plus x minus 2. Now to factor this, as a reminder, this is going to turn into a binomial times a binomial. These first two terms must equal x squared when multiplied. What do they both must... What do they need to be? They both have to be x, because the only way this is going to work is if x times x equals x squared. Now my last two terms have to equal 2 when multiplied. That means one of them needs to be a 2, and the other one needs to be a 1. I can't think of another way to multiply two numbers together to get a 2. 2 times 1 equals 2. But we do have this negative. So when I multiply these together, it has to be negative, so one of them has to be a negative. But when I add them, they have to be this positive 1 that's right in front of this x. So when multiplied, they give me a negative 2, but when added, they give me a positive 1. It would have to be a positive 2 and a negative 1, which means fully factored, this would be sine x plus 2 times sine x minus 1. That is our guess and check method. That works usually if there's no number in front of our lead term. And this is a nice, easy, like 2. But guess and check might not work for our next one. Our next one says let's change things to x's just to make it a little easier to do. If I gave you a problem that was like 8x squared minus 10x minus 3, let's talk about why we can't guess and check this. You might be able to get lucky. But there's multiple ways to get 8. We could have a 1 and an 8. We could have a 2 and a 4. It could be a 4 and a 2. That goes along with our 3 would be a 1 and a 3, but you have to check a lot of different stuff. So it becomes more cumbersome to guess and check. So here's where we need to have a method. I do not care how you factor these. If you don't like the method I use like a snowflake method or whatever method you use it. If you have no method, then probably pay attention to what I'm about to do. I'm going to use factor by grouping. It's the only way I've ever taught it. It's the only way that I do it. Factor by grouping requires you to write something off to the side. We're going to write a column for A times C and a column for our B term. 8 years ago when we started doing this, my class came up with air conditioning and Beyonce, and it just stuck. You have your air conditioning column and you have your Beyonce column. For factor by grouping, use an air conditioning column and a Beyonce column.
What's the correlation?
if we look at the terms here, we could put a letter by each thing. We can say this is my A term, B, and C. It goes in order, so everything makes sense. So if I talk about A, I'm talking about 8. If I'm talking about B, I'm talking about negative 10. C is negative 3. So if I need to do A times C, that will be 8 times a negative 3, which would equal a negative 24. Beyonce stands alone, so you just put a negative 10 there.
Destiny's Child.
That's right. She got out of that real quick. See, you got 3 things. She got out. All right. So you have your A times C. This is your air conditioning column. Is also your multiplication column. You're looking for 2 numbers that multiply together to give you negative 24. So you could just make a whole list of things that give you 24. But we also have to be careful because it must add to negative 10. So I'm looking for just randomly picking numbers that might work. So you can make your whole list. You can go 1 and 24, 2 and 12. Can anyone think of 2 numbers that multiply together to give you 24, negative 24, but add to give you negative 10? We're looking at 12s and 2s maybe? Is that what I hear? Negative 12. Well,
Yeah.
let's just do 12 and 2 for just a second. Now, we know one of them needs to be negative, right? So at this stage, I'm like, okay, I know 12 minus 2 is 10. Oh, I need it to stay negative. So we're going to do negative 12 and a positive 2 because negative 12 plus 2 equals 10. I don't think that's that hard to do. It just takes practice. Air conditioning Beyonce column. Just takes practice going back and trying this. Now, the rest just kind of falls in place. Now, the reason we did this, so negative 12 plus 2 equals negative 10. We're going to use this to split this apart. We're going to split this apart. That's the whole point of making sure it equals 10. We're going to split this apart. So we're going to rewrite this equation as 8x squared. And it doesn't matter if you put the negative 12 or the 2 first. So I'm going to put negative 12x plus 2x minus 3. All of that equals 10x, negative 10x. Didn't do anything wrong. I just broke it apart into 2 things that equal the same thing. This is where it's called factor by grouping. I just created 2 equal groups. I have a group here, and I have a group here. Your job is to factor the biggest thing you can out of each group. So if I'm looking at 8 and 12, what's the biggest number I can pull out of 8 that I can also pull out of 12? 4. What's the biggest thing I can pull out of x squared and x? X. 1x. I could pull out 1x. Can someone turn off their phone, please? So now remember, I'm factoring out a 4, so I'm looking at what times 4 equals 8? Well, that's going to be a 2. What times x gives me x squared? That's an x. What times 4 equals a negative 12? That's a negative 3. You can also think about division. Negative 12 times 4 equals that negative 3. X is just x divided by x is 1, so I just have 2x minus 3. What's the biggest thing I could pull out of 2 and 3? We could pull out a 1. I do write a 1. You don't have to, though. I'm going to write the 1 because you kind of need to understand something. So that's going to leave me with 2x minus 3. Here's why I like factor by grouping. This is not a coincidence. If you do factor by grouping correctly, both of those are the same thing. Now we're going to do a very mathematical term, and it's called smoosh together the 4x and the 1. We're going to smoosh together the 4x and the 1. I will explain why we can do this in a second. So we have 4x plus 1 times 2x minus 3. And this is now fully factored. Now I'm just going to replace my x's with the sign of v. And we'll have 4 times sine v plus 1 equals 2 sine v minus 3. It takes a long time to explain. If you do it by hand and practice it, it doesn't take that long. It's a really quick process. The hardest part is just coming up with these two numbers, but that's every process. No matter what process you have to come up with these numbers. Questions on any step I took?
No.
Then I'll talk about this magic step that happens here, the smoosh together. If you don't care why it works, then just plug your ears. Let's say I had 2x plus 3x. You would tell me that's 5x, right? Mm-hmm. It's 5x because of the same rule I did to there. I actually have 2 plus 3 x's. It's actually the distributive property. So if you're adding something that's the same ending, you can add the first two things. That's all that happened here. I got the same things. I can smoosh together the front things because they're attached by multiplication. Questions on that? All right, so we really